Good morning, ladies and gentlemen. Welcome to another episode of Dave Does Math from Home. We got an exciting one for you today. Today we are wrapping up Chapter 2 in Calculus. Today's lesson is about continuity, Section 2.6. Continuity is an extremely important idea in calculus, but it's very sort of backgrounded throughout most of calculus. Once we finish up with Chapter 2 here, we're going to start doing derivatives, which is where we're going to start using these limits to do like some real calculus and on some real functions. And throughout that entire rest of the course, the idea of continuity is going to be very important because we can only take derivatives of functions that are continuous. So we need them to be continuous, but mostly we're just going to kind of assume that they are, because we're doing calculus on them, and it's not going to come up directly much. But I do want to cover it here today so that we can know what it is, what it means to be continuous, and then as you do derivatives, we can think about why something like that would be important. So let's get right into continuity. Much like limits, we're going to kind of have two versions of continuity. We're going to talk about like what continuity looks like graphically, visually, on graphs like this. And then we're going to talk about what continuity looks like analytically when you're doing that to functions, equations, formulas, that sort of thing. So let's start with graphically, since we already have a graph here. The super easy version of continuous graphically is, can you draw it without picking up your pencil? So this is sort of like the basics of continuity. So you can think of like your standard parabola. You can draw a standard parabola without ever picking up your pencil. The parabola is continuous. Sine waves, you can draw sine waves without ever picking up your pencil. Sine waves are continuous. This thing I have right here, this is not something that you can draw without picking up your pencil. If you were going to trace this or draw this for the first time, you could draw this chunk without picking up your pencil, and then you would have to stop, and you'd have to pick your pencil up off the paper, put it back down over here, start drawing again. Then you'd have to pick up your pencil again for this little hole, and keep drawing on the other side of this hole, and then you put the hole there. So this graph cannot be drawn without picking up your pencil. This graph is discontinuous. The bad news is we're mostly interested in continuity at points or in regions. So this is discontinuous at this point. We'll say that this is x equals 2. This function is discontinuous at x equals 2 and at x equals 5. These are the 2 points of discontinuity. And there are different kinds of discontinuity, and we're going to talk about that later. But this is discontinuous at 2 and at 5. If you want to talk exclusively about x values that are less than 2, so if you're going to talk about everything to the left of this, you could say that that much of the graph is continuous. This part is continuous. So it's continuous on the interval from probably, if it keeps doing this, from negative infinity to 2, on this interval, it's continuous. From 2 to 5, it's continuous. From 5 to infinity, it's continuous. But at 2 and at 5, it is discontinuous, because those are the points where you would have to pick up your pencil to finish drawing it. So let's talk about the kinds of discontinuity we see here, because that will also be important. There are two flavors of discontinuity. The first flavor of discontinuity is called a removable. a removable discontinuity. And in this context, removable basically means fixable. So essentially, a removable discontinuity means if you change one point on the function, can you make it be continuous? Can you create continuity by changing one point? If you can create continuity by changing one point, then the discontinuity is removable, fixable. So that's what's going on here at x equals 5. As x approaches 5 from the left, we look like we have a function value here. Let's say that this is 3, y equals 3. It looks like it's going to 3 from the left. It looks like it's going to 3 from the right. If we just make it equal to 3 by filling in that hole, then we would have a continuous function. So that's how we would fix that. That's what makes this discontinuity removable. Two things I want to mention about this. You can think about this as like fill in the hole. That's really what a removable discontinuity is. It's a hole that you can fill in to connect the function. The other thing I really want to emphasize here is that the language I just used to describe this discontinuity is as x approaches from the left and as x approaches from the right. Hopefully, at this point, we all recognize that language very clearly as the language of limits. So essentially what this means is the limit exists. If we have a limit, then we could make the function value equal to beat that limit, and then we would be all set. That's what it means to fix this. You set the function value equal to the limit value, and then the discontinuity is removed, the function is connected. All that really requires is for the limit to exist. That's really what a removable discontinuity means. So there's a lot of different ways to think about this. All of these different ways to think about this are equivalent, I'll say. They're not identical because they involve thinking about this in sort of different ways, but they are equivalent to each other. So the other kind of discontinuity we have is, if it's not removable, then it's non-removable. Non-removable means we cannot fix it. We cannot create continuity by changing one point. And the limit does not exist. And that's what's going on here at x equals 2. Here we have a function value. The function value is, I don't know, -3 or something. We have a limit from the left. We have a limit from the right. Those are different things, so we can't fix this. There's nothing we can do to make these connect. Or we can't make them connect by changing one point. We could probably change a chunk of the function. Like if we changed this entire region to go up here instead, then we could fix it. But that's a huge change. When we say if something is fixable, we're talking about changing exactly one point and nothing else. This cannot be fixed by changing one point. You will always have this big separation here. So you can think of this as like a big gap. And we can also think about this as the limit does not exist. So that's what's going on here. These are non-removable. So yeah, these non-removable discontinuities come from if you have something like this, which is a piecewise function, where left of 2 it has one equation and right of 2 it has a different equation. You get non-removable discontinuities from stuff like that. You also get non-removable discontinuities from things like vertical asymptotes. An asymptote will create non-removable discontinuities that cannot be fixed by changing a single point. These holes, these removable discontinuities, these don't really come from asymptotes. These usually, you usually see these in situations where like you have a rational function and you can cancel a factor from the top and the bottom, but you still keep that domain restriction. That's where you get these holes, and the official name for these holes is removable discontinuities. So that's what's going on graphically. Let's talk now about how to do this analytically. Analytically, and much more officially than sort of graphically. Like graphically is a nice way to talk about and sort of get to know something, but like all the official stuff usually comes from the analytical versions. Excuse the interruptions, I have a misbehaving cat. It needs to be wrangled. So, analytically, we can talk about continuity as sort of having 3 pieces. For something to be continuous at a point, let's say continuity at a point A. Because we already kind of talked about how things are continuous on certain regions and discontinuous at points or other regions. So we're going to talk about continuity at a point A. Continuity at the point A means 3 things. First, the function exists. So if we want it to be continuous, we need to have a value for the function. Second, the limit as x approaches a, f of x exists. So we need to have a function value and we need to have a limit. And if we want this thing to be continuous, we need these things to match. The limit as x approaches a of f of x equals f of a. So let's just quickly remind ourselves what these things mean. F of a is what the function is actually doing at a. The limit as x approaches a of f of x, this is what the function looks like it's doing at a. If what the function looks like it's doing matches what the function is actually doing, then we have continuity. If it looks like it's going to hit 3 and it actually hits 3, that's what continuity means. And we talked about this situation a lot when we first introduced the idea of limits. I think one of the first things I said is most of the time the function is actually doing what it looks like it's doing and there's no problems. That's because most of the time we're going to be playing with continuous functions that are sort of well behaved and smooth and like they do what you expect them to do. They actually do what you expect them to do, and that's what makes them continuous. So this is the official sort of definition of continuity, and in a lot of the homework problems it'll ask you to sort of evaluate when a function is discontinuous, it'll ask you to sort of evaluate why it's discontinuous. And sometimes it's discontinuous because the function value doesn't exist, and sometimes it's discontinuous because the limit value doesn't exist, and sometimes it's discontinuous because they both exist but they don't agree, or some combination of them. So familiarize yourself with sort of these 3 conditions for continuity so you can pretty clearly evaluate what's missing from them. So like in the last graphical example we were dealing with, we had this function here, and then here, like this. We said this was 2, and this is 5 on the x-axis. 1, 2, 3, 4, 5. In this case, the discontinuity at x equals 5 is because these two conditions are not met. We have a limit value, but f of a doesn't exist and they don't match. If we change the function so that there's a point up here, now we have the function exists and the limit exists, but they don't agree. So it's still discontinuous because of this third condition. At x equals 2, we have the function value exists. It's down here, probably -3 or 4 or something. The limit does not exist, so that's where it's breaking down. And if the limit doesn't exist, then of course they don't match. And if we want to talk about at x equals 3, whatever this point is, we have the function value exists, the limit exists, they agree, all three of these are met, so it's continuous at x equals 3. I said we were going to talk about this analytically, and then I kept talking about a graph. I'm going to cut this video, we'll make another one, and then we'll talk about continuity analytically. Stay tuned.